All right. Good morning, everybody. It's time to get started. Thank you for being with us this morning. It's the first session of the day, and I appreciate the fact that you woke up a little earlier to be with us. So my name is Julian. I'm a tech evangelist. I focus on AI and machine learning, and today we're going to talk about deep learning with TensorFlow and SageMaker, but we're going to talk especially about the fantastic use case that AIM and Mobileye have built. And this is one of the deepest TensorFlow sessions I've seen. So hang on, right? And I hope you have coffee. So let's get started. So we're going to cover a few things. So I'm going to say a few words about TensorFlow on AWS as a quick intro, and then I'll hand the stage over to AIM, who's going to explain what the use case is for TensorFlow and SageMaker at Mobileye, and he's going to go very deep into how they actually scaled their computer vision and autonomous driving workloads on SageMaker. Again, very, very cool content. And then I'll be back, and I'll go through a demo showing you how to use all those new SageMaker services that were announced yesterday, almost all of them, and how to use them with TensorFlow and specifically Keras. Okay, so pretty long demo, again, pretty deep. So hang on to your hats. Let's get started. TensorFlow. So who's running TensorFlow in production today? All right, some people, thanks. So you know all about it probably. It's a popular open source library for machine learning and deep learning, and the main API is in Python with some level of support for other languages. The initial version of TensorFlow, so TensorFlow 1.x, has been out for a while, and it uses a programming model called symbolic execution, okay, where you have two well-defined steps. First, define an execution graph using variables, placeholders, tensor operations. So define that thing completely, and then compile it, which really means transform it into an optimized representation, and then feed data to it and train and save the model, etc., etc. And you can do this in different ways. You have a low-level API. You have a, I hate to call it a high-level API. I'll call it a mid-level API, estimators. And you have a high-level API in the form of Keras, right? Which I love very much. So you can do those three things, but the process is always the same. Define the execution graph and then run it. And that's fine. There's nothing wrong with that. The tiny problem about this is the graph that is actually being trained is very different from the graph you define because all kinds of fancy optimizations have been applied. So it makes inspecting, understanding, and debugging the training process a little difficult, right? And I guess that creates that black box perception on deep learning generally. So TensorFlow 2.0 came out at the end of September, and the biggest change is they now use a different programming model called imperative execution. The actual term used by TensorFlow is eager execution, but that's the same thing. And people get confused by imperative execution. It's like, so what's this thing now? Okay, well, it's just code, right? It means define code by running it. Okay, so when you run Python code, NumPy code, you are using imperative execution, right? So it's just a fancy word for a quite simple thing. So this is great because now we can build networks, we can run them, we can inspect them, we can debug them, just like we would use normal Python code. Okay, so you can use the Python debugger, you can have breakpoints, you can just run and test and debug the code just like normal Python code. So it's a more natural way of working with code, and it's an easier way to just get better results. And much to my joy, Keras is the preferred API, right? So Keras is now fully integrated into TensorFlow, and it's actually the preferred way of building models. Okay, and you can go from super high level for quick experimentation all the way to super custom if you really need to have a custom training loop and custom layers, et cetera, et cetera. But Keras will let you do all of it and using eager execution, right? So that's a very good move. As it happens, we have tons of customers using TensorFlow. And you may have seen this number, that 89% of deep learning workloads in the cloud run on AWS. And of course, TensorFlow is a large chunk of this. It's the most popular library. And well, 85% of all TensorFlow workloads in the cloud run on AWS. Okay, which I think gives us a responsibility to make sure TensorFlow runs very well on AWS. And actually, we have one of my colleagues in the room is leading the TensorFlow development team at AWS. So if you have deep technical questions, he'll be happy to answer them. TensorFlow on SageMaker is a first-class citizen, right? How could it be otherwise? So we have built-in containers on SageMaker for TensorFlow, for training and prediction, for CPU, GPU. They're open sourced on GitHub, so you can go and check them out, run them, etc. We support all the 1.x versions, up to 1.15, which I believe is the latest and last one for 1x. And 2.0 is coming soon. And I'm going to get shot if I give you a date. So I'm just going to say coming soon, and you can make what you want of it, right? And when we say TensorFlow on SageMaker, it's not just TensorFlow, right? It's not just pip install TensorFlow and get to work. It's TensorFlow with all the nice tools you expect, like TensorBoard for visualization, TensorFlow serving to deploy models with the model server. And of course, we bring all the SageMaker goodies, right? And I'll show you some of them in my demo, and Chaim will go ultra deep on some of them. Things like local mode, training locally on your local machine, script mode, automatic model tuning using spot instances, pipe mode using EFS or Lustre for low latency training, elastic inference, and the list goes on, right? And I guess it just gets bigger every day. We have performance optimizations. We believe the TensorFlow version you are running on SageMaker is the fastest available, right? Because of all the great work that my colleagues are doing on TensorFlow, optimizing for GPU and CPU, also working with Intel, et cetera, et cetera. And last but not least, you get distributed training using either the native TensorFlow mode called Parameter Server or Horovod, this really cool open source project that lets you really scale your training jobs. And by the way, we're contributing quite a lot to Horovod as well. So if you watched the keynote yesterday, you saw this family of new announcements. So let's quickly go over them. So the first one is SageMaker Studio, a machine learning IDE that lets you see all your notebooks and all your experiments and all your monitoring and all your debugging jobs in the same place. Okay, so a nice IDE to have everything in the same place, which means I can stop jumping from one notebook to the next, working on different parts. So very nice productivity improvement. One of the important bits in Studio is a service called SageMaker Notebooks. That brings you the ability to spin up notebooks immediately without having to create notebook instances just like you would in SageMaker. And also you can easily share them with colleagues. So you can share not just the code, but the actual context of the notebook, including the cells that have already been run and the storage, et cetera, et cetera. And you can also switch really easily from one hardware configuration to the next without having to rerun the notebook. So it's in preview, but I'm hoping it goes GA very quickly because this is, again, for productivity, it's a great boost. SageMaker Debugger lets you configure debugging rules on your training jobs. I'll show you how this works. And it will alert you that certain unwanted conditions are taking place in your training job. SageMaker Experiments is just a way to let you organize thousands, tens of thousands of experiment and training jobs, automatically storing metrics and metadata for all those jobs, and using a simple SDK, letting you query all those experiments, compare them, etc. And of course, this is integrated in Studio with nice visualization. Model Monitor is exactly what the name says. It's a simple way to monitor your endpoints in production. So you can enable data capture automatically. And then you can just, using again the SDK, look at the data that was captured, compare it to a baseline that you had already designed, and find problems like data drift or data quality issues, etc. So again, really, really cool service. And the last one is called SageMaker Autopilot, and it's our AutoML service that will automatically identify the best algorithm, the best pre-processing script for a given problem, for a given data set. And it's going to train and optimize that model, and it auto-generates notebooks that show you everything that happened and notebooks that you can run. So it's absolutely white box AutoML. You can actually understand how the model was built, and you can retrain it yourself if you like. Okay? So I'll show you most of those in the demo. But now it's time for Chaim to get on stage. Thanks again for flying all the way from Israel to be with us and sharing this really, really cool use case. So please, let's have a round of applause for Chaim.
Thank you. Thank you, Julian. Mic working? Okay. Good morning, everyone. Nice to meet you all. My name is Chaim Rand, and I am a machine learning algorithm developer at Mobileye. In my role at Mobileye, I have the privilege of working with SageMaker on a daily basis, and I am delighted to be here with you today to share some of my experiences. What I'd like to do is tell you a story that I have titled, Making Amazon SageMaker Work for You. It's an exciting story about how my team at Mobileye adopted the SageMaker service, the ways in which it enhanced our development capabilities, some of the challenges we faced along the way, and how we overcame them. It is a story of courage, creativity, and intrigue. Here's a quick spoiler just to keep you guys awake. By adopting SageMaker, my team managed to reduce our development time by as much as a factor of 10, from several months to under a week. In some cases, by using SageMaker, we were able to develop solutions that we simply did not have the ability to develop beforehand. Here is my story. I'd like to start by telling you a little bit about Mobileye and the need within the company that the SageMaker service fills. Mobileye was founded back in 1999 with the express goal of using computer vision technologies to revolutionize the transportation industry, make roads safer, and save lives. Actually, one of the things I enjoy most about working at Mobileye is that it's pretty simple to explain what I do. Contrary to trying to explain something like blockchain or quantum supremacy, what we do is simple. We save lives. Mobileye was acquired by Intel in 2017 for a whopping $15.3 billion and is now officially known as Mobileye, an Intel company. The lawyers wanted me to emphasize that. Not Mobileye, Mobileye, an Intel company. In fact, every time I say Mobileye in my talk, I should be saying Mobileye, an Intel company. But I'm going to spare you guys, just to find your place in your heads. So how does Mobileye save lives? We have developed a range of software solutions that run on a proprietary family of chips called IQ. These days, these are predominantly found in advanced driver assistance systems, otherwise known as ADAS. These systems might include features such as collision avoidance, lane departure warning, and adaptive cruise control. You might be familiar with such systems from your own car or from another car that you've been in. As a matter of fact, every single Las Vegas taxi that I've been in this week had a Mobileye system installed in it. So take a look next time you're in a taxi. Mobileye has partnerships with 25 automakers, including most of the world's largest. Driver assistance systems rely on external sensors for identifying the objects in their surrounding environment. At Mobileye, we rely only on simple monocular vision cameras for our sensor input. Not only does this enable us to significantly reduce the cost of our product, but it also frees up other sensors, such as LiDAR and radar, for redundancy and validation. The input from the camera is fed into deep neural networks that are trained to identify just about any road-related artifact you can imagine. These include road users, such as vehicles, pedestrians, and bicycles, road semantics, such as traffic lights and road signs, road boundaries, such as curbs and construction cones, and road geometry, such as driving paths and speed bumps. All these capabilities are collectively referred to as sensing technologies. Rather than elaborate on any one of them, I'd like to show you a few brief video samples. Let's warm up with this clip of a car driving through the streets of Paris. Notice how it's able to identify the drivable space marked in green, as well as vehicles, pedestrians, road signs, and traffic lights marked using bounding boxes. I imagine that some of you may have already seen clips like this before, so let's move on to something a little more complex. Here we are using a more sophisticated deep neural network in order to provide full pixel-level segmentation of the scene. Each pixel is marked with one of 13 labels, including road in green, vehicles in yellow, road boundaries in red, guardrails, curbs, and so on. No introduction to Mobileye would be complete without a few words about autonomous vehicles. Our goal at Mobileye is to continuously increase the level of autonomy of the vehicle up to its eventual full autonomy. Mobileye views full autonomy as relying on three technological pillars: sensing, mapping, and driving policy. Sensing refers to the sensing technologies we have just discussed for identifying road artifacts. Mapping refers to the autonomous vehicle's ability to identify its precise location on a map in a process called localization. By precise, I mean extremely precise, down to within 10 centimeters of the exact placement of the vehicle within its lane, far more precise than the GPS-based solutions in circulation today. The driving policy makes driving decisions based on the input from the mapping and sensing technologies, decisions such as which path to take, when to accelerate, when to brake, when to switch lanes, and so on. Let me show you a short clip that demonstrates our autonomous vehicle technology in action. There's a lot going on here, so let me start by explaining what you're about to see. On this top, you can see a bird's eye view of all the information that the vehicle has collected about its surroundings. This includes all the objects it's identified using the sensing technologies, how it has localized itself on the map using the mapping technologies, and the path that the car has chosen to take, shown in light blue, using the driving policy technology. As you can see, the car needs to negotiate a pretty challenging left turn. You can see the car approaching the intersection and needs to wait for an opening in the traffic that will enable it to cross to the other side. I think you'll agree with me that this would not be easy even for a human driver. It sees the car slowing on the left and on the right, and there she goes. I want to remind you that this is based only on monocular vision cameras, no LiDAR and no radar. The landscape of autonomous vehicles is fascinating, and I encourage you to learn more about Mobileye's plans in this space, including our unique positioning and roadmap. You can tune in later to session AUT 307 by Mobileye VP Tal Bobayev, and also visit our website to learn more. So how does SageMaker fit in? I will answer that in chapter 2 of my story, Enter SageMaker. So as you can imagine, Mobileye has a very wide variety of deep neural networks, many different architectures of all shapes and sizes. One property of most of our DNNs is that they train on very large data sets. We have mountains of data, up to 200 terabytes for some of our networks. At a high level, our development cycle is pretty standard. We first label our mountains of data. We then use TensorFlow to train our DNNs on the labeled data on one or more GPUs. And finally, we take the trained model and customize it to run on our proprietary chip, IQ. In the past, my team would perform the training on dedicated GPUs on Mobileye premises. However, there are a number of obvious drawbacks to this method. Firstly, there never seemed to be enough GPUs. Oftentimes, I would come to my manager, his name is Yishai, and say, Yishai, I need 30 GPUs to test 6 different models with 5 different sets of hyperparameters. And Yishai would say, I'm sorry, there are only 5 GPUs available, 6 if you pick up my laundry. Imagine the frustration. Imagine the impact on development time. Secondly, as the sophistication of our networks grew and the sizes of our data sets grew, we started to run up on all kinds of data capacity limitations. Our in-house infrastructure simply could not keep up with our demands for more and more storage location. Imagine the despair. And lastly, the constant challenge of trying to stay up to date with the latest hardware and software would just make us want to pull our hair out. As you can tell, Exhibit A. Naturally, we started to look for alternatives. The constraint being that any alternative would need to comply with our existing data development pipeline and have to keep our IP safe. This is where SageMaker came into the picture. So I wanted to title this slide, What I Love About Amazon SageMaker. But my wife said to me, Chaim, you gotta keep your emotions in check. So here are some of the things I really, really like about SageMaker. SageMaker offers unconstrained capacity. This means that I can spin up as many training sessions as I'd like. If I need 30 GPUs, I can use 30 GPUs. If I need 100 GPUs, I can use 100 GPUs. You guys are developers, so I don't need to tell you. When I heard this, I felt elated, like a kid in a candy store. This ability to easily scale up the number of training instances is one of the main things that contributed to our ability to reduce the duration of our development cycle as much as by a factor of 10. SageMaker supports a wide variety of instance types, new GPUs and old GPUs, new versions of TensorFlow and older versions of TensorFlow. So I can choose single GPU instances and multi-GPU instances. So I can choose the data instance to best fit my needs. When you start working with SageMaker, you can immediately tell that the SageMaker team has done their best to make the porting process as simple as possible, both in the ways that they have tuned their APIs to the needs of us developers, as well as in the abundance of documentation and sample code. In our case, despite the sophistication of our models, we were up and running within just a few days. SageMaker keeps my data secure. I'm not going to pretend to know any more about this other than that my data security team will let me use it, which is really all I care about. But above all, what I really, really like most about SageMaker is the pipe mode. So much so that it deserves a chapter of its own. Chapter 3, SageMaker Pipe Mode. So what is pipe mode? Pipe mode is a mechanism based on Linux pipes for streaming your data directly from S3 storage to your training instance. The old way of doing this is to download all the data from a central storage location, such as S3, to local storage on the training instance, such as EBS. This needs to be done each time you want to spin up a new training session and may cause a significant delay to the training start time. If you have large data sets, as we do, you may also incur significant storage costs, again, for each training instance. In SageMaker, this method is called file mode. If you have very large data sets, never use file mode. SageMaker pipe mode avoids this by essentially feeding the data directly from S3 into the algorithm as it is needed. This is shown in this nifty little graphic. Our data is stored in one location in S3. One or more training sessions are configured to point to it. and start to pull the data via the pipes directly into the training algorithm as it is needed. No local storage required. This ability to stream data directly from S3 to the training instances has some very important implications for us. Firstly, this removes any limitation on the size of our data set. Recall that we often train with mountains of data sets that can reach up to 200 terabytes. We can now store all of this data in S3 and stream it directly to the training instances without ever having to worry about local storage costs or constraints, and without any download delay. Earlier, I told you that adopting SageMaker enabled us to develop solutions that we did not have the ability to develop beforehand. This is the main reason why. If in the past, we were constrained by all kinds of storage limitations, now we could store as much data as we wanted on S3 with its virtually limitless storage capacity and just feed it directly into the training algorithm. This also means that our data storage and training environment are now decoupled. We can spin up as many training instances as we like and have them all point to a single copy of our data in S3. No need to maintain multiple copies of our data. Now, lest you should be wondering, how do I feed a pipe into my network? Do I really need to start managing Linux pipes? SageMaker comes to the rescue with a pipe mode implementation of the TensorFlow dataset interface. TensorFlow dataset is an abstract API that represents an input pipeline of a DNN. By wrapping a pipe mode with an implementation of the TensorFlow API, TensorFlow dataset API, not only does SageMaker hide all the low-level pipe management from you, but it also automatically gives you implementations of all of the dataset utilities, such as shuffling, mapping, batching, and interleaving. No 400 series session would be complete without a few lines of code. So I will try and make this as painless as possible, but it really is simple. Configuring your SageMaker job to run in pipe mode requires only a few lines of code to both your deployment script and your training script. In the deployment script, when instantiating your SageMaker TensorFlow object, you must set the input mode to pipe. Then create a dictionary where the keys are the names of the pipes, and the values are S3 path prefixes. This dictionary is then passed into the SageMaker TensorFlow fit routine. In the example here, we are creating a single pipe called train that points to the shown prefix path. This means that all files in S3 that start with this path will be fed into the pipe. Pipes are identified by their names. As we will see in a moment, our training script will refer to the pipe it will read from by its name. In the training script, you need to set up a pipe mode dataset. This is no different than setting up any other TensorFlow dataset. The pipe mode dataset constructor takes as input the name of the pipe, which we have set to the name of the pipe we have just created, and the record format, which is the format of the data passing through the pipe. In this case, we have chosen TF record, a popular binary format defined by TensorFlow for storing data records. So we've seen that configuring your training session to use pipe mode is quite simple, but we did face some challenges adjusting our training flow to using pipe mode. In Chapter 4, I want to tell you a little bit about these challenges and how we overcame them. The three challenges I want to discuss is how we adjusted our dataset to working with pipe mode, how we adopted our training flow to the sequential nature of pipe mode, and how we overcame the limitation on the number of pipes per training session, which today stands at 20. So let's start with the first challenge. The first challenge had to do with converting the format of our data. Pipe mode dataset supports a limited number of formats. These include CSV, protobuf, and TF records, all standard and popular formats. In order to enjoy the goodness of pipe mode dataset, we would need to undertake the daunting task of converting all of our mountains of data to one of these formats. How did we solve this? So actually, This turned out to be a huge blessing in disguise. Faced with the need to modify our data creation flow, we decided to port this stage of the development to AWS as well, ultimately leading to an enormous acceleration in our data creation time and thus to our overall development time. We did this by using the AWS Batch service, and by running up to hundreds of thousands of virtual CPUs in parallel. Each CPU was programmed to generate one portion of the output dataset. In our case, a single 100 megabyte TF record file. This is actually a useful tip. When deciding how to organize your data in S3, you should choose a file size that will maximize the throughput on the pipe. The recommendation we received from AWS was to divide our data into files roughly of size 100 megabytes. And indeed, we found that working with files of greater or smaller scale to be less optimal. Moving our data creation to the cloud had a mind-boggling impact on our data creation time, reducing it from many, many days to just several hours. Okay, let's take a quick break from pipe mode, because there's one slide that I simply have to show you. So as it turned out, the solution to converting our data turned out to be one additional step in porting our entire development pipeline to the cloud. This diagram summarizes our development cycle today, and I think is an excellent example of how different AWS services can be combined to support an end-to-end solution. We start with raw data and label files stored in S3 and managed with DynamoDB. These are fed into highly parallelized TF record file creation processes running on AWS Batch. The generated files are written back to S3 and then fed into the training sessions running on Amazon SageMaker. The resultant DNN is then fed into a deployment script, which performs post-processing operations on the model weights, including pruning and quantization, and prepares our model for deployment on our proprietary chip. This script we also run on SageMaker. I will note that while we run our own proprietary deployment script, SageMaker offers the Amazon SageMaker Neo service for optimizing DNNs for target hardwares, and also offers support for deploying a model directly on SageMaker. The main takeaway from this slide is that porting our DNN training to Amazon SageMaker turned out to be just the first step in porting our entire development pipeline to AWS, and the additional significant optimizations to our development time came from moving some of the other portions of our development to AWS. Back to pipe mode. The second challenge that we faced had to do with the sequential nature of pipe mode. In the past, we had relied on our ability to randomly access any record in our data set for functionalities such as shuffling and boosting. Let me clarify that by random access, I'm referring to the ability to freely access any record within the data set as shown in this graphic. In pipe mode, you do not have this freedom. In pipe mode, the only data you can access are the next records in the pipe. How did we overcome this limitation in pipe mode? So let's start with shuffling. Shuffling one's data is a very common practice in the world of DNN training and often critical for success. In the past, we would shuffle the input by simply choosing a random ordering on our data set. Of course, to do this, you needed to have the ability to freely access all of the records in a data set. In pipe mode, this method is prohibited, as the only records you can access are the next records in the pipe. We overcame this limitation by introducing shuffling on a number of levels. Most importantly, we configured our pipes with the Amazon SageMaker Shuffle Config class. This ensures that the dataset files associated with each pipe are shuffled before each epoch. Configuring your pipe with the Shuffle Config class requires a one-line change in the SageMaker deployment script, as shown here in red. This covers shuffling between the TF record files. We add an additional level of shuffling at the training batch level by using the built-in TensorFlow dataset shuffle routine. This is how we solve the shuffling challenge. We also used to rely on random access to our data for boosting. Boosting is a method that can be employed for increasing the representation of underrepresented data. For example, suppose you are tasked with creating a DNN that identifies vehicles. Suppose that you run a few rounds of training and find that your model succeeds in identifying most vehicles successfully, but consistently fails to identify pink cars. You go back to your training data set and you realize it's no wonder that you're failing to identify pink cars, as only 5 out of the 1 million records in your data set include pink cars. One way of addressing this is to boost the pink cars in your data set, to artificially increase the representation of the pink cars by inserting the pink cars multiple times during each epoch. When you're able to freely access your entire data set and can point to the pink cars in the data set as illustrated, this is a fairly simple task. But how do you do this when your input is sequential, as in pipe mode? We chose to solve this by creating dedicated pipes for the data that we wanted to boost. In the example of the pink cars, we would create 2 separate pipes as illustrated on the bottom of the slide, one for the pink cars and one for all the rest of the cars, and then combine them together using a TF dataset interleaving API, such as sample from datasets, which combines different datasets while allowing you to apply a weight to each one. This solves a simple case where we have just one underrepresented data type. But what if we have many different subsets of data, each with their own associated weight? This brings us to the last of the 3 challenges we faced: overcoming the limitation on the number of pipes. SageMaker currently limits the number of pipes per training session to 20. Now you might be wondering, why would anybody need more than 20 pipes? So we have just demonstrated how multiple pipes can solve the problem of underrepresented data. Let's return for a moment to the example of the pink cars. Suppose now that your model succeeds in identifying pink cars, but fails to identify pink trucks, or fails to identify pink trucks in the rain. Suddenly, we might find ourselves using 4, 5, or 6 different pipes for boosting underrepresented data with different weights. You'll notice that I've used drawings created by my daughter rather than stock images. This was so as not to upset any of the copyright lawyers. It's a totally true story. Another factor that might increase the number of pipes is distributed training. Harvard is a popular framework for performing distributed training with built-in support in SageMaker. However, one drawback to Harvard is that it requires dedicated pipes for each GPU that is being used. This means that if you were using 3 pipes on a single GPU, and now want to use Harvard to run distributed training on an 8 GPU instance, you would now need to configure 8 times 3, that's 24 pipes, and you are suddenly above the 20 pipe limit. So how do we overcome this limitation? Our solution was to use pipe mode manifest files. Using manifest files is an alternative way to configuring pipe mode, in which we specify a list of files that we want to have streamed on the pipe rather than providing an S3 prefix. Instead of setting an S3 prefix and relying on SageMaker to find all the files that match the prefix, in the manifest file you provide a specific list of the files you want. So for example, when we use manifest files, we can perform boosting, such as pink cars, by simply listing the same file containing the pink cars multiple times in the manifest file. This feature was critical for us in keeping the number of our pipes below the limit. To summarize, manifest files enables finer control over the data at the cost of having to create and manage an appropriate manifest. Configuring pipe mode to use a manifest file is once again a one-line change to the SageMaker deployment script, as demonstrated in red. Here, we set the S3 data type to manifest file and add the shuffle config setting so that the list of files in our manifest are shuffled before each epoch. Closing remarks. So I've chosen in my story to focus on the pipe mode feature and how we implemented it. But there are a number of additional things to consider when using SageMaker. I've written a blog to go along with this talk in which I expand on my story and describe how we addressed some additional questions. For example, should I employ distributed training? And if so, how do I choose the optimal number of GPUs? What framework should I use? And how do I maximize resource utilization? How do I take advantage of spot instance to reduce cost? How do I use TensorBoard and other benchmarking tools when using SageMaker? How do I overcome the challenge of debugging a failed training session on a remote environment? I encourage you all to check out the blog and share your own insights and experiences. In summary, I cannot overemphasize the degree to which adopting SageMaker enhanced our development capabilities. Pipe mode offers us a great solution for training with our mountains of data. Our development time has been reduced significantly thanks to our ability to run many training sessions in parallel and as a result of porting our data creation to AWS batch. We did face some challenges, but we're able to overcome these by using the SageMaker and TF dataset APIs creatively. This has been a story about how we made SageMaker work for us. I hope I have convinced you that you too can make SageMaker work for you. Thank you.
Amazing. Amazing. All right. So let me switch to my laptop and we can see some of this stuff in action. Okay. All right, can you read in the back? Yes? Okay, thank you. All right, so in the time left, and sorry about the fire alarm test, it looks like the fire marshal decided this was a good time to have a fire alarm test at the MGM, so we had some lights, right? Good thing it's done. In this example, which you can find on GitLab right now, so if you have a laptop, you can just go to GitLab and follow along. I'm going to show you how to train a Keras script on an image data set. So I'm not using 200 terabytes of images. I wish I could do that. So maybe you need to share some data with me in S3. I'm using a simple data set called fashion MNIST, right? I'm sure you all know about MNIST, and we're all very tired of those digits. So this is a drop-in replacement for MNIST using fashion articles. This was put together by a company called Zalando, and that's the kind of stuff they sell on their website. So it made sense for them to build that data set. Okay, so I'm going to start from there. Try to build an image classifier for this data set, showing you how to use a lot of SageMaker features along the way. Okay. So first of all, of course, I need to download the data set. Download it to this notebook instance here. And let's take a quick look at the Keras code. So, like I said, Keras is the high-level API for TensorFlow, and it's now the main API for TensorFlow. And here I'm using a very, very important feature called script mode. Okay, we'll see more about it. So script mode is a SageMaker feature that lets you use the exact same code that you would run on your laptop inside the TensorFlow container in SageMaker. Okay, and when I mean the same, I mean the same. Okay, and I'll prove it. So you can run this code locally on your laptop and in SageMaker without changing a line because of this script mode feature. And it all boils down to the ability to receive hyperparameters as command line arguments, because this is how that code will be invoked inside the TensorFlow container. and the ability to read those 4 environment variables that will be set by SageMaker, telling you where's the training data, where's the validation data, and where to save the model, and how many GPUs you have. So if you write your training code this way, you can run it on your laptop this way and move it absolutely unchanged to SageMaker. So I think that's a critical capability. Okay, so we take some arguments, hyperparameters and SageMaker parameters. We load the training set, the validation set from their location. Then we do basic normalization because these are grayscale images, so we want to normalize pixel values between 0 and 1. And then we build a very simple CNN, and this is where Keras absolutely shines because you have all those pre-existing layers that you can use. So 2 convolution blocks with activations and a fully connected block at the end for classification, okay? Then I compile the model. I use the SGD optimizer. I'm adding some metrics here from the Keras metrics package because I'm building a classifier, so I like to know about maybe the F1 score, for example. I could set up image augmentation, just like Chaim said, but on this data set, obviously, it makes no sense. It's just going to slow things down. But for real-life workloads, I'm sure this is critical. And then just train the model, print some metrics, and save. Okay, so this is vanilla Keras. There isn't a single line of custom code here. It's only the ability to read those environment variables that SageMaker will set. Make sense? Hopefully, yes. All right, so that's my code. So just to prove it, right, I'm running it locally. I'm shelling out, as you can see here, and I'm running it in this Jupyter notebook. And this is how you would run that code on your machine, right, while you're debugging. So training for 1 epoch. So I just had to take care of setting those environment variables pointing to my local data and the local directory to save the model. Okay, and I can run this code, and I can see, it's running fine. I'm just running for 1 epoch, so it doesn't really matter what kind of accuracy I get. But okay, I run this on my laptop, and that's fine. Now, there's another feature in SageMaker called local mode. So local mode will use the TensorFlow container locally. Okay, so we're actually pulling the TensorFlow container to your local machine and running on your local machine. So again, that's the nice next step after testing locally, local, right, I call it. You can test locally with the TensorFlow container to check that your code runs fine inside the SageMaker container for TensorFlow, okay? And you only do that, you use the usual TensorFlow estimator for this, passing the location of the code, and that's the only trick you need to do, right? Set the instance type to local, which means I don't want to fire up manage infrastructure on SageMaker. I want you to use this machine, okay? And so it's pulling the TensorFlow container locally, and it's using local data, as you can see, right? And it starts immediately as well. So you save time by not firing up that managed instance, and you also save money by not doing that, okay? And I can see here, how the code is invoked inside the TensorFlow container, okay? Which is exactly the way I want it. It's invoked as a script with hyperparameters as command line arguments, and that just works in exactly the same way, right? So script mode is absolutely how you should write your code here. All right, and then it trains for a bit, and it saves the model. So now I know this code works in the TensorFlow container. So now let's upload the data set to S3, right? And let's train on managed infrastructure. But of course, it's a 400 level session, and we have all those new capabilities to play with. So I'm not going to just train that vanilla job here. First, I'm going to use spot instances because money and budgets are important. So we want to have the least expensive possible training job. So setting spot instances is as easy as this, right? And I'm going to enable Amazon SageMaker debugger by saying, hey, while you're training this, can you please keep an eye out for loss not decreasing and overfitting, right? And these are built-in rules, and I could look for exploding tensors, and I could look for vanishing gradients, and I could build my own rules. So what this does now, when you fire up that training job, as you can see in the log, it gets the training job going on that managed instance, and in parallel, it's running a debugging job Okay, and this is actually based on this other service called SageMaker processing that we announced yesterday. So it fires up a job in parallel that's going to look at tensors saved by the training job, okay, and looking for those unwanted conditions that I configured. Okay, so the training job goes on, and in parallel, it's saving tensors to S3, and the debugging job is reading those tensors and looking for those weird conditions that I configured. Okay? So it trains for a bit. There we go. All right. Okay, so it trained for 470 seconds, but I use Spot, right? So I only pay for 141 seconds. So that's 70% discount, right? You like that? Everybody likes that, right? Who doesn't want a 70% discount? And I'm not paying my bills, right? You are, thank you. So, okay, so now this training job is completed, but I want to know if the debugger actually found stuff here. So I can describe the job and say, show me the status of those debugging rules, please. So what does it tell me? It tells me, well, there was an issue on loss not decreasing. So there was some part of the training process where loss did not decrease. So you could say, is that a problem? Because sometimes, loss can go up and down then again. It's a very jittery process. So we would need to take a look. Is it a transient condition? And probably here, yes. Or is it really, you reach some kind of a plateau and loss is really too high and not going down anymore. And overfitting did not happen. Okay, so that's great. Suppose I wanted to investigate further. I would just grab the tensors that have been saved during the training job, and I can see them in S3, a whole bunch of files. So not really human readable, but that's okay, because what I want to do is this. I want to create a trial, so use those tensors in S3 to inspect further, right? Just one single API call. I can load my tensors, and I can see, okay, these tensors are available, so I could inspect F1 score over time, or I could inspect loss over time, right? And I could keep zooming in like this, okay, printing the values for loss at periodic steps during the training process. And you can spend your life zooming here, okay? Hey, by the way, did I write code for this? No, right? Did I have to modify my Keras script for this? Nope. Zero code, right? Fully managed. So this is available on Keras. This is available on TensorFlow, MXNet, etc. And you can customize it. Here I'm going the noob way, right? In the interest of time, but you can go ultra deep on this. So I could deploy my model. Say, okay, it's a good model, and I could use this elastic inference feature where instead of deploying to a GPU instance, I can deploy to CPU instance accelerated by fractional GPU acceleration. We call those things elastic inference accelerators. I'm not going to do it here, but in general, you can get GPU-like performance at 70–80% discount. So if you have small, medium models that don't require a full GPU instance, elastic inference is a fantastic cost-saving opportunity again, right? Okay, let's keep going. So I'm not deploying this. I want to tune further. So I want to use automatic model tuning, which has been part of SageMaker for a while. So as all those parameters are actually command line arguments, I could, using script mode, I could say, hey, I want to explore ranges for epochs and learning rate and batch size and the number of convolution filters and the size of the dense layer and dropout, okay? So I could do architecture search using automatic model tuning and trying to come up with a high accuracy model automatically here. And this is called automatic model tuning. Try, find the needle in the haystack. I want to maximize validation accuracy. That's my metric. And while we're at it, I'd like to also extract all these different metrics which are in the training log, and I can give regular expressions for SageMaker to find them. Okay, and these will be stored in my tuning job as well. Okay, but the target metric, the objective metric I want to optimize on is accuracy. Okay, so I just configure my estimator again. I'm just removing the debugging rules, right? That's the same thing. Still using Spot, but no debugging rules. And then I put everything together. Here's the estimator. Here are the parameter ranges. Here's the metric. And please run 20 tuning jobs 2 by 2. Okay? So fire up 2, figure out what kind of accuracy you get, and then apply Bayesian optimization. Pick 2 new sets of hyperparameters. Train again, optimize again, pick again, optimize again, etc. Okay? So we're going to do 20 jobs here. So I kick things off, right? And I'm going to see those 20 jobs running. If I switch to the SageMaker console, I'm going to see 20 training jobs, okay? Obviously, I'm only interested in one, right? The best one. But which one is the best one? So I can use this new service called SageMaker Experiments, which is natively integrated with automatic model tuning and Keras. And once again, 0 code needed, right? Just run my code and all those metrics are pushed automatically. So I can use the experiments SDK, say, hey, I want to grab all the metrics that you have for that tuning job and please put this in a pandas data frame, right? And I can see my 20 jobs, okay? And I can see the hyperparameters to the right that were tried for these specific jobs, okay, some extra information, and I can see the final objective value. So fine, I could explore those 20 jobs. And again, this plugs into SageMaker Studio when you have all the eye candy in the world to look at this, but I'm more of an SDK guy, sorry. Oh, no, I shouldn't run this. Okay, no worries. Okay, so I can sort them out, and I can figure out that the best job it's actually the last one, which is funny. So that tells me I should have run a little more than 20 jobs. I can find the name of that job, okay, and I can deploy it, okay, because I know this is the best so far. And I'm going to deploy it, and I'm going to deploy it with data capture, okay, because I want to monitor what's going on that endpoint. And that's the last of those services I want to talk about today, because SageMaker Model Monitor. So I want to capture input data and output data on that endpoint. So define a location in S3, and you guessed it, right? 0 Keras code. I need this on a t-shirt, right? 0 is my favorite number when it comes to lines of code. And set up a data capture, say, capture data on this endpoint, put it in S3. By default, it will capture 100% of input data and output data. But, of course, it's configurable. Then I just call deploy on my hyperparameter object, and that deploys the best model, okay, by default. Okay, so wait for a few minutes for this model to come up. Then I can predict with it, so I can take random images from the validation data set. Here I take 10, and I use the predict API from the SDK, which is HTTP posting those images to the endpoint. Okay, and it looks like we're doing okay with this simple example. So now I'm going to score the full data set. So I'm taking all the images in the validation data set, 250 by 250. And I push them to the endpoint, and I store all labels and all predicted labels, okay? So it takes a few seconds, and then I can build a confusion matrix, which I call the confusing matrix, because if you've never seen this before, it's confusing. And this shows me how I'm doing, right? Reality on the left-hand side, the true labels versus the predicted labels on top, okay? So ideally, we would have a maximum diagonal and zeros everywhere else, okay? Unfortunately, that's not happening in real life. So we see the diagonal, so most zeros are predicted as zeros and most ones are predicted as one. And these are class IDs, by the way, of course. And it looks like class 6 is a real troublemaker, right? There are lots of confusions here between class 6 and other classes. So we would have to look at mispredicted examples and keep figuring out what's going on. Okay, so pretty good model anyway. And I did capture data, right? So if I list S3, I'm seeing those objects here. I can copy them locally and look at one of those. And this is what I see, right? And I see the input for each data sample, and I see all the predictions. So here, of course, you see pixel values, right? This is how it's a JSON encoded input. with the pixel values for each image that is being pushed. Then I could train a baseline on that data set, and I could ask Model Monitor to alert me if it sees deviations in data quality compared to the baseline, if it sees data drift, etc., etc. Okay? But I'm, oh yeah, perfectly on time, amazing. And I could then delete the model. So once again, this is on GitLab. This is my Twitter account if you would like to send me feedback, please, or questions. So there we are. Thanks again to Chaim for a fantastic talk, right? I cannot believe you're not doing this every day, right? This is really great. These are all the new services that are out there. I wrote a few blog posts on those. They're on Jeff Barr's blog, so you'll find them. And here are some resources to get you started. I will share the deck on my Twitter account later today, so don't worry, you will get those slides. And if you have questions, feel free to ping me on Twitter, LinkedIn, anywhere else. Here are other breakouts. We're actually doing another session tomorrow with Fannie Mae, a different use case. So if you want to look at this. And actually later today, I'm doing a deep dive session recapping all those new services. So it's going to be a different demo. I'm guessing the Venetian session is full by now, but they have plenty of overflow rooms. So AIM410-R, if you want to see, if you want to learn about those services in more detail with different demo, please join us. And yes, AWS.training is a good place to go. And there are plenty of learning opportunities as well. So thank you very much. Chaim, thank you so much. Toda rabba, right, as I'm going to say. Please come back on stage. Thank you for being with us. I'll stick around, and Chaim, you will stick around for questions. But we have to leave the stage now. Thanks again. Your questions welcome, and have a great day. Thank you very much.